Section 4.1 is composite functions. Here's the definition of a composite function. Given two functions f and g, the composite function, denoted by f, composed with g, and that's how you would read that. It's not fog, even though that's what it looks like, is defined by this function. F composed with g is equal to f of g of x. And the way that I want you to read that or interpret that in your mind is f of g of x. Basically what this means is whatever comes out of g goes into f. A more appropriate or mathematical way of saying this is that the domain of g may consist of this whole big old thing right here. The domain of g gets mapped to this range of g. You plug x's in, you get y's out. But some of these elements that are in the domain of g may give you values in the range that are not in the domain of f. Well, what comes out of g, right here, the range of g, has to be put into f. So where these overlap, that then becomes the domain of our composite function. So let's look at an example here, evaluating a composite function. You should have seen this before in high school, so this part should be reviewed. If it's not, speak up quickly and let me know. So remember, we name our functions for the same reason we name our children, so we know which one we're talking about. So here, f of x is going to be the function that squares something and multiplies that result by 2 and then adds 3. G says we're going to cube something, multiply that result by 4, and then add 1. So the first thing we're asked to find right here is f composed with g of 1. Whenever you're dealing with composition and you want to evaluate the composition, first rewrite that function using the embedded parentheses. So f composed with g of 1 is actually f of g of 1. And then we're going to simplify this. F is the function that's on the outside, and we're going to simplify what's on the inside. This says go to your function g, and in place of x, plug in a 1. Well, g's over here. G says you take 4 times something and then cube it and add 1. Well, that something now is going to be 1. That's what we're plugging in here. 1 cubed is 1. 1 times 4 is 4, and 4 added to 1 is 5. So now what we're looking at is f of 5. We just simplify the arithmetic here. So now we go to our function f, and in place of x, we're going to plug in 5. So that's going to be equal to 2 times 5 squared plus 3. So we plug in the 5 right here, and 5 squared is, and 25 times 2 is 50, and plus 3 then would give us 53. So the final answer here is 53. So f composed with g of 1 is equal to 53. What happens if we change the order of the functions? Are we going to get the same thing? Well, does order matter? Sure it does. So this is going to give us what when we rewrite this using embedded parentheses? So I leave the g alone, and then in place of f of 1, I'm going to say, well, f says you take 2 times something squared plus 3, and that something in this case is 1. Simplify what's on the inside and you get 5. 1 squared is 1 times 2 is 2 plus 3 is 5. So g of 5 is going to give us 4 times 5 cubed plus 1. What's 5 cubed? 125 times 4 is 500 plus 1 is. Makes sense? Alright, can we compose a function with itself? Sure we can. The nice thing is the operation or the method that we go through doesn't change. We're going to still rewrite this using the embedded parentheses. So that's f of negative 2. So we take our negative 2 and we plug it into the function f in place of x. Well, f says you take 2 times something squared plus 3. What goes in place of x now? And negative 2 squared is, times 2 is, and 8 plus 3 is 11. So now what do we do? Plug in the 11 in place of our function f. F still does the same thing. We're just plugging a different number into it now. So 11 squared is 121 times 2 is, plus 3 is 245. And then we do the same thing with g. You can compose a function with itself. We just proved it. So we look at g of negative 1. What does g do? G says you take 4 times something cubed plus 1, but in place of x we're going to plug in negative 1 cubed is negative 1 times 4 is negative 4 plus 1 is, so now I'm looking at g of negative 3. G says you take 4 times something cubed and add 1. What do I plug in now in place of x? Negative 3 cubed is negative 27. Negative 27 times 4 is negative 108 plus 1 is. Alright, so evaluating these, notice when you put numbers into these composition functions, you get numbers out. If we were to put variables in, guess what we get out? Variables. It's the nice thing about functions. Whatever you put in is what you're going to get out. Next problem, we want to find the domain of f composed with g. So this is going to be finding all of the values of x that are going to be valid here. First of all, let's rewrite this using the embedded parentheses. F composed with g of x is equal to f of g of x. What is g of x equal to? 2 over x plus 1. What is the domain of 2 over x plus 1? X cannot be equal to negative 1. That's true still, no matter what you get after you compose f and g, because g is what we started with. Now we need to simplify this. What is f of 2 over x plus 1? Well, what does f say you do to a function? You take 3 over that function, or whatever's in there. In this case, it's 2 over x plus 1. And we subtract 5. Now we want to simplify this. How are we going to simplify this? Do you see how I plugged this in place of x right here? Okay, that's where the x was, right here. So now we simplify this. And I'm going to do that by multiplying both the numerator and the denominator by x plus 1 and distributing it. There's several different ways you can go about simplifying this. This is just the one that I choose to do. So I'm going to multiply the numerator by x plus 1, and I'm going to multiply the denominator by x plus 1. And when I do that, then I'm going to end up distributing that denominator across to both of these terms. So that's going to give us then 3x plus 3 over 2 minus 5 times x plus 1. Can I simplify this further? So this is going to be 3x plus 3 over 2 minus 5x minus 5. And when we combine like terms in the denominator, we get 3x plus 3 over negative 5x minus 3. So what can x not be equal to with the composed function? 3/5. So the domain of this composed function not equal to negative 1, because negative 1 is not in the domain of g. And if a number is not in the domain of g, it cannot be in the domain of the composition. Also, x cannot be equal to negative 3/5, because when we composed these two functions and we simplified it, when x is negative 3/5, we end up with a 0 in the denominator of the composed function, and that can't happen. Remember, the domain of any polynomial function is all real numbers except where x is undefined. This is a rational function. The function's not defined if the denominator is 0. So where this number came from was setting this denominator equal to 0 and solving for x. This sign, it means it belongs to the set of. It's like a curve with a line in the middle. Blown up, it looks a little bit like this. It's set notation. Any real number x, given the condition that x is a real number and x is not equal to negative 1 or negative 3/5. Next, showing that two composite functions are equal to each other. This does not happen often, but occasionally it does. If f of x is equal to negative 2x plus 1 and g of x is equal to negative 1/2 times x minus 1, show that f composed with g and g composed with f are equal to x. So here we're going to start with this side, and then we're going to show that it's equal to here. We're going to start here, end here, and we're going to get them both equal to the same thing. So we have f composed with g of x is equal to f of g of x. That's just the definition of composition. Then we start replacing things from the inside out. So we're going to replace g of x with what g of x is equal to. So that's going to give us f of negative 1/2 times x minus 1. So now we go to our function f, and f says you take -2 times something and add 1. Well, what am I going to put right here in the place of the x in my function f? -1/2 times x minus 1. Well, what's -2 times -1/2? That's going to be 1. So that's going to give us x minus 1 plus 1. And what does that equal to? Yay, we started there. We showed it was equal to that. Now we're going to do the other one, g compose with f of x. Well, that's g of f of x. So that's going to be g of, and g says we do what to a function? We're going to take -1/2 times that function minus 1. That function in this case is -2x plus 1. Do I need these parentheses here? I just put them there because I wanted to show you that x was that whole expression right here. What I have in the bold blue right here is g of x, -1/2 times something minus 1. -1/2 times something minus 1. I did that to show you that I just dropped inside in place of x right here what I had in the parentheses here. That's what's in place of x. So now I can simplify this. -2x plus 1 minus 1 is, because the plus 1 and the minus 1 cancel each other out, and that's equal to x. We're done. We've shown it here. We've shown it here. They're both equal to the same thing. It's unusual that this happens, but whenever you compose a function with another function and you get out what you put in, these two functions have a special relationship. We call these inverses of each other. In this situation, f and g are inverses of each other. For example, squaring a square root, that would be an inverse operation. Apparently, this function and this function are inverse operations, demonstrate inverse operations. A calculus application, finding components of a composite function. Find functions f and g so that if you compose these two functions and you get it equal to another function h, you end up with this. Well, what function is on the inside? G. G is, see, when we have this, that's f of g of x. So we're putting g inside of a function. Looking at this, can you tell which one of the functions is on the inside and which one's on the outside? G is this, x squared plus 1. If g of x is equal to x squared plus 1, what is f of x equal to? X to the 50th, because f says you take something and raise it to the 50th power. That's going to come in handy when you start taking the derivatives in calculus and you start using something called the chain rule. You don't have to know what that is now. I just want you to be able to spot it. When the time comes, you will be ready to understand what the chain rule is. It's not today. All right, finding the components of composite functions again. Now here's f composed with g equals h, and here's what h is. Can you spot what f is and what g is? F of x is equal to 3 over x squared, and what is g of x? It's what's on the inside. G of x is what's on the inside if you're composing them in this order. By the way, when you rewrite these functions using the embedded parentheses, notice the letters stay in the same order. That might help you keep it straight. Helped me when I was a student. Anyway, that wraps up section 4.1.